Thank you very much, Petronella. And thank you organizers also for thinking of me. I thought about speaking today of a topic that is certainly very relevant in scientific computing, fast solvers, but it has not received that much of attention, in my opinion, for the integral fractional Laplacian. So that's the topic of the talk today. And this has been developed in collaboration with these three people that you see here in the first slide. So after spending a few minutes, only a few minutes on background material about the integral Laplacian and regularity and error estimates, I'll move to the core of the talk, which is about adaptive multi-level preconditioning. All right, so let me move to the beginning of the talk, which is the definition of the fractional Laplacian in integral form. This is sort of well known to most of us. So here is the problem, defining a bounded domain that I'm going to assume that is a Lipschitz domain, typically in R2, but it can be, think of this in Rn or Rd. The function u is going to be 0 outside. This is the way we pose the Dirichlet boundary condition. And the operator is written here in integral form, as you can see in red. And this is interpreted in the sense of principal value because the kernel of the integral is singular. C here is a constant that is simply a normalization factor that makes this definition consistent with the definition by Fourier transform. Space where this is defined is the so-called H tilde S space, which are functions with this norm, semi-norm if you like, bounded. Here is the semi-norm induced by this integral, and the functions are 0 outside the domain. This space is H tilde S, is not the regular HS, which are functions defined in omega. These are restrictions to omega of functions that globally have this semi-norm bounded. But because the functions are 0 outside the domain, they satisfy Poincaré inequality for every S. And so then this bilinear form here, which is associated with the Laplace operator, it has, as you see, the normalization factor, is the one we use to define the weak or the variational formulation of the problem written here for functions, test functions in HS tilde. So this bilinear form is symmetric, is continuous in coercive because of Poincaré inequality. So Lax-Milgram guarantees everything we want from the functional setting point of view, existence, uniqueness, and stability. So the next key question is the regularity, and this has been an issue for some time. I just go quickly over it. You see, it goes back to 65, and more recently to 2015. And the issue is that even for boundaries that are as smooth as you like, there is a limit in the regularity of a solution. It cannot go beyond HS plus a half minus epsilon, no matter what F is. So this limit of regularity is due to the boundary behavior. And in fact, this example, there is a very simple and probably one of the only, or the very few examples, explicit examples of solution, it's a radial solution in a ball of radius R, tells you that the behavior at the boundary is like the distance to the power S. And this is exactly what you expect in this problem for every domain, even with curved boundaries, even infinity boundaries. This function here does not belong to HS plus a half, so this regularity is actually sharp. There is more. This, what I just said, is in Sobolev spaces. There is regularity in Helder spaces by Rossotton and Serra that I will be using later. And even more recently, together with Borthagaray, we were able to do some work on Besov spaces that I would like to mention very briefly because it enters later. You see, in this regularity, it's important that the domain satisfies the exterior ball condition, which basically for polygonal domains, it means that the domain has to be convex. We can relax that. So without the exterior ball condition, for domains that are Lipschitz, we can prove the following regularity. F in L2, then the functions for S bigger than 1/2 are in Besov spaces with regularity S plus a half, which is consistent with this regularity I mentioned here. The epsilon is because this is in Besov spaces, and if you go to Sobolev spaces, you will lose an epsilon. And if S is less or equal to half, then you have the pickup to S that is consistent with the previous regularity. So this is a new result and is inspired in a technique by Savare, developed years ago. So now about the error estimates, which is the next thing that I like to mention briefly, we have basically two types. Let me set up the framework first. We have a mesh, tau h. We have a space, VH, of continuous pieces of linears, and the discrete formulation that gives us a UH. And so because this is a scalar product in this space, we have a best approximation result without any constant. So everything now depends on how well we can approximate our function within the space HS tilde. And that means accounting for non-locality and the boundary behavior that I just described. So there are two types of results. In quasi-uniform meshes, as you can see, this goes back to 17, but there is some recent progress. We get power h to the 1/2 for smooth domains, say infinity domains, and for ellipsis domains, we get this. Okay. The question here is that there is a reduced rate even for linear functions, and this is because of the boundary behavior that can be compensated by using graded meshes as discussed by Acosta and Borthagaray, also in 17. If the meshes are sort of refined towards the boundary with this law, then the linear order is restored. And as you can see in the numerical experiment here, for the simple example of a ball that I mentioned earlier, these results are sharp. For uniform meshes, you see the 0.5. For graded meshes, you see essentially order 1 for every possible S in the range from 1 to 9, 0 to 9. However, this result here in graded meshes is not really constructive. It's not clear that you can construct meshes like this, although in practice you can. So I'd like to mention something very recent, which is a constructive approach. And I call it adaptive approximation, and here I'm thinking about bisection grids that will come up later. So think of the interpolation error that I split in local patches. These are the first ring or first patch of the element, using results of Furman. And each of these local terms in HS can be bounded by interpolation. So now with this estimator for the error over a triangle, we run a greedy algorithm, which basically, given a tolerance, marks elements for which this estimator is bigger than delta, refines those elements and perhaps more elements to keep conformity with this routine refine that implements bisection, and keep doing that until this set of marked elements is empty. So this algorithm, I'll call greedy, terminates because every time we cut an element, we reduce the size of H. And upon termination, we get the convergence rate in terms of degrees of freedom. This is degrees of freedom that is consistent with this convergence rate here. However, this procedure is constructive, and I would like to say the proof certainly is constructive and is based on the Helder regularity by Rossotton and Serra I mentioned earlier. Okay, so let me now move into the core of the talk, which is the discussion of fast solvers. I call it robust additive multi-level preconditioning, and the word robust, I sometimes call it uniform, refers to both the dependence on the number of levels or refinements and the value S, the parameter S of the Laplace operator. So this is the setting. Suppose you have a space. Now this V is going to be our finest element space, which is a sum of spaces, VJs, of different levels. They don't have to be uniform. They can be refined locally, so they can be graded, spaces associated with graded meshes. VJs, we have an operator which is called VJ. Say this is a scaling, okay, by the size of the mesh. Think of a scaling, a negative power or a positive power of the mesh size. And this is the actual additive preconditioner that we get by adding these operators VJ. Okay, so think of VJ and you give me a function, I scale it with the power of H. I will give examples right in a moment. But the general theory says that if we use this as a preconditioner, which means we want to estimate the condition number of the product BA and we like that to be uniform, we need to estimate the maximal and the minimal eigenvalues. And there are two steps to follow, so-called stable decomposition that you see here. For a given any function in the space V, defined as element space, we have to find a decomposition Vj, the sum of the Vj's is V, satisfying this estimate. The sum of this, I would say, weighted L2 norms is bounded by the HS norm, and that gives a lower bound for the minimal eigenvalue. And boundedness, for every decomposition, the HS norm of the sum is bounded by the sum of the scale L2 norms. This constant C0 and C1 should be independent of the levels and S, and together these two estimates gives us an estimate of the condition number. That's the general theory. So how does it apply in our case? Now, let's think about it just before we look into this transparency. The usual BPX preconditioner, which is based on a decomposition like this with scaling, is well understood, well studied for the Laplace operator and variations of the Laplace operator of integral order. However, the fractional Laplace operator that we have right now, Laplacian to the S, is like the Laplace operator for S close to 1. And in fact, for S going to 1, it converges to the Laplace operator. But for S, the fractional exponent going to 0, the operator converges to the identity. And the identity has a very different behavior from the Laplace operator. In fact, the identity is associated with the mass matrix, and we know that if we scale the mass matrix, we do a diagonal preconditioner, we get an optimal preconditioner with condition number 1. This is not what we need to do for the Laplace operator. So if we want something uniform in S, that will the same algorithm that will work for every S, including the endpoints, it doesn't seem obvious that the usual preconditioner, BPX, will work. Our key result is this one that I call S uniform decomposition, that tells you that if you have nested spaces, it doesn't matter how they are, they can be uniform, they can be corresponding to nested, to refined meshes, it doesn't matter. And you have, the only thing that matters is that they are nested, and you have the QKs that are the L2 projectors. So you look at these slicing operators. So these are projections on the VK spaces, orthogonal to the previous ones. The sum of this gives me a decomposition of V. So this scale norm, you see the S here, that is what we would expect for the Laplacian, for the fractional Laplacian, is equivalent to this infimum, which is what we know for the BPX preconditioner, except that there is a factor here in red. And I want you to pay attention to it. This factor is usually innocuous if S is away from 0. And we don't see it, we don't care. But if S goes to 0, then the exponent goes to 0 and the denominator goes to 0. And so, in a sense, it penalizes the coarser scales. And this is something that is consistent with my comment before, that the coarser scales, when we get close to the identity, should play much less of a role, and for the identity should play no role. So this is the result that we obtain. And together with S uniform interpolation, so with constants independent of level and S, and local inverse estimates for fractional norms, then we can do the theory. But before showing you the theory, I'd like you to take a quick look at this table, where you see uniform meshes and graded meshes. Okay, this conjugate gradient method using the regular BPX, and this is the one that is scaled to take into account S. And you can be so across S, even for S very small, both for uniform and graded meshes. Okay, now let me move into the BPX for quasi-uniform meshes, which is the simplest possible setting. Here, we have meshes that I call with a bar because they are uniform, and spaces that I call also with a bar because they correspond to the uniform meshes. Now I'm concrete with the operators. The BKs bar are these scaling operators. So they correspond to taking the L2 norm and scale it. This is what you would expect for the BPX, except that there is this scaling here that is associated with the coarser scales, and is to make this uniform in S. The gamma tilde is related to gamma. It doesn't necessarily have to be. It's of the order of gamma square. Doesn't have to be. But since it changes, it is not always gamma or gamma square, we call it gamma tilde. So here is the additive preconditioner induced by these scalings. So this is what you would expect for BPX. Coarser, finer scales and coarser scales. This is what you would expect, except for this factor. With this BPX, with this preconditioner, we can prove that the condition number of B times A is uniform, both in J, the number of levels, and S, the exponent of the fractional operator. And the way this works is by proving boundedness. Boundedness is usually based on the so-called strengthened Cauchy-Schwarz inequality, which means you look at functions in two different spaces, say with different scales, and this measures somehow the angle between the spaces. The spaces are not orthogonal, but as the scales separate from each other, you see this exponent here, gamma, raised to a power, which is the difference of the levels. So that goes to 0. So this shows the angle between the spaces. So this is the usual strengthened Cauchy-Schwarz inequality, except that the usual proof doesn't work. You cannot integrate by parts here. What we have done is based on the Fourier transform and the fact that the definition of the HS norm sitting here is equivalent to the Fourier definition. Now, if you use this formula naively, then you have a problem. Say, suppose you want to estimate this sums of the BKs in terms of the scales L2 norms. Okay, so suppose you put this, you use the inner product. So you do the inner product of this times itself, and it's written here. And then you just use Cauchy-Schwarz from this formula, okay? So what you see here is a factor that has to do with the spectral radius of the associated matrix with these gammas on the diagonal and going away from the diagonal. So the associated matrix for this inner product, scalar inner product here, this discrete inner product is 1 divided by 1 minus gamma to the S, which again shows you that if S goes to 0, this blows up. And that is not the right way to go. So with a slightly better analysis, you can prove this estimate, which is consistent with our S uniform estimate. No scaling for the finest scale and scaling for the coarser scales. And that gives an upper bound for lambda max. For lambda min, you need to do the space decomposition, which is usually based on these slicing operators. These are the two projections on the spaces V, K, bar. And it's just this estimate here that these slicing operators scale, and you do the sum of the L2 norms. This is equivalent to the HS norm. This is a proof based on our S uniform interpolation estimate. With this, we can prove this estimate, which is the decomposition, the actually stable decomposition, that given a V in the finite space, you can find the decomposition VK. The V is a sum of VKs with this bound. The way to do that is to combine this norm here with our S uniform decomposition that I mentioned before. That was a critical thing that we developed in this work. So this leads to a lower bound for the minimal eigenvalue. Put it together with the previous one for the upper bound for the maximal eigenvalue, we get the uniform preconditioning. Okay, so now let me move to the most delicate part, which is what happened with graded meshes. Now here the situation is the following. I'm thinking about bisection grids, and this is the way usually they are producing an adaptive procedure. Say you have a mesh, I call it Tj minus 1, and you add a bisection to get the new mesh. So what is this bisection, which I call compatible? So in 2D here is a cartoon. Suppose you have two triangles and you want to cut them. So you want to cut this triangle. So you look at the edge associated with, this is the edge that you need to cut. So you would like to cut here, but then you permission to the neighbor to see if that edge is also the cutting edge for the neighbor. If it is, you just cut. This is a completely local operation, a compatible bisection. But if the neighbor happen to have a different side, for instance, this is the edge for the neighbor, then you cannot cut. The neighbor has to ask permission for the neighbor of the neighbor. So this enters a recursive procedure that may have maybe a long chain. Eventually, you end up with a compatible patch, and that is our VJ. And from that patch that might be far from this, you come back and join with successive compatible patches, compatible bisections. So this procedure is such that in these recursive steps, you never have a non-conforming mesh. You always have a conforming mesh. And the bisections are always compatible. So associated with the bisection, you have 3 points. As you see, you have the bisection point and the endpoints of the segment, I call right, left and right. Associated with these 3 points, you have 3 bases or hat functions. I call them phi, j, q. And the 3 points form what I call this bisection 3 point. Okay, so for each bisection, you have a space of dimension 3. In addition, when you are finished with your mesh, you have a fineness mesh that might be very irregular, okay? You may have very coarse elements somewhere and fine somewhere else. In our application, all the fine elements are near the boundary. The space is called V, is the finest space, is the span of functions that have vertex P. This is the internal nodes of the finest mesh. And I call VP the span of each single hat spaces. This is the full finest space. Okay, having said this, we have a natural space decomposition, the finest space and the intermediate space. For each of them, sort of borrowing from what we learned before, we have the natural scalings for the finest mesh and for the intermediate scales, and a natural BPX preconditioner. Okay, this is for the finest scale, and this is for the intermediate scale with a factor that I mentioned and I alluded to earlier. Is this the right object? Now remember, our spaces now are, you know, we don't have uniform spaces, or there are refinements that might be fine somewhere and maybe coarse somewhere else. So what we can prove are 2 results. One is boundedness, that for every function V in the space with this decomposition on this, okay, finest and intermediate, we get that the HS norm is controlled by the scales L2 norms. Okay, here is a proof for those that are curious, particularly maybe the younger folks that are listening to me, that I will skip. The most tricky part, and this is really difficult, is the stable decomposition. As usually, this is complicated. And it's not as simple as we might get. As you see, given a function, we have 3 components now. The fine component and the intermediate components, which are not just supported on these spaces Vj. There is a component here that is also supported in the VPs, but will be less or equal k. The generations of the VJs here had to be of the order of k. So this has to do with the fact that this spaces Vj may contain elements. But for all purposes, you may think of this k star to be 0. In fact, it's bounded uniformly. And also we can prove this bound, okay? The scales L2 norms are bounded by the HS norm of V. Okay, this is a very non-trivial step, but this induces this preconditioner. This part is the finest part, and these 2 are the intermediate coarser parts with corresponding scaling. And this induces a lower bound for the B hat. The problem is that this B hat is not our B. So the next step is to prove that these are spectrally equivalent. So the B hat that I mentioned before and the B that I mentioned even earlier are spectrally equivalent. And that leads to a lower bound for the lambda mean and our theorem that says that we can, in fact, control the condition number of B times A by something uniform in the levels and S. And to conclude, let me show you some results, some numerical results. These are done in a square. This is for uniform grids, and you can see here the behavior of the precondition conjugate gradient, the number of iterations for different levels, so it's sort of very stable, and it's not very sensitive with respect to S, okay? It doesn't misbehave for S small, as I mentioned earlier. And here is the same for graded bisection grids. Here you have maybe a sample of grids for levels 6, 9, 12, and 15. And here are the results. Again, in red, you can see the performance. This is very stable in terms of levels and also in terms of S. As you move to the right, you see the numbers don't increase. In fact, they are quite stable. Okay, so in summary, and here you have the references about what I talk about, I show you that additive preconditioner, a BPX preconditioner, but if you want it to be uniform for all the range of S, on the range S equal to 0, you need to modify the usual recipe, and the theory that shows uniform B times A becomes much more delicate. This is contained in this paper that is about to be finished. I mentioned 2 publications that are related to the same topic. And here is there are some additional results, regularity, and survey papers that might people that might want to learn about fractional diffusion, okay? These papers do not contain the results about BPX, but they contain a lot of discussion of the setting, error estimates, and so on. And with this, I'd like to conclude and thank you for your attention.